All right, we're back. Nico, tell us about the Big Bang.
Back. The Big Bang. Oh, well, that's a long, complicated subject. What exactly do you want to know about, like the TV show?
No, that's a TV
do you
show.
Want to listen? Well, we want to talk about the actual explosion.
The actual
huh?
explosion.
Well, okay. So we don't really know. To be perfectly honest, we talk a lot about the Big Bang, but we don't really know what the Big Bang is and exactly what happened at the Big Bang. What we know is that the universe seems to have expanded, as you know, as you think about the evolution of the universe into the future. The universe is expanding. So if you play the movie backwards, then the universe is contracting. Right? It makes sense?
Right.
And you can actually observe light that was emitted many millions of years ago by looking at, very distant stars and very distant galaxies and the light that was emitted shortly after this so-called Big Bang. But at some point, we can't really observe back enough into the past to see what was happening at the explosion. You would imagine that if everything is expanding into the future and you play the movie backwards, essentially the universe came from a point, right? And that point must have been a very special point, a point with like an amazing amount of energy and pressure. And if the universe is supposed to be the size we observed it today, then clearly there had to be some sort of violent explosion that led to what we observe today. But in reality, we don't really know if that explosion really took place, and if all of this of the universe was really a point, or maybe it was not a point. Maybe it was just a little tiny ball, the size of. Smaller than the size of an atom, so maybe the size of an electron, or smaller than the size of an electron. We don't know. We don't have data, so we can only speculate about what happened far enough into the past where this point of infinite energy emerged. In fact, there's theories that say that this point didn't emerge at all. That there's this entire other history of the universe that continues if you just keep on pushing into the past, and the universe maybe is cyclic, maybe go through cycles, right? I mean, if you think about religion and if you think about philosophy, typically you find sort of two lines of thought. There's like the Western view of time, where you think of time as linear, right? Cause and effect.
Right.
Time moves forward, and it's a line. Okay, but if you think about Eastern religions, that's not really how it is. In a lot of Eastern religions, time is more like a circle. There's this idea of reincarnation. There's this idea that nothing is sort of created or destroyed. Everything comes back onto itself. Okay, and if you want, in cosmology, there's also these two lines of thought that maybe the universe didn't start at a point. Maybe there is such a thing as before that point existed, right? Maybe everything is cyclic, and we don't know right now which one of those two hypotheses is right. So we're making, guess what? Measurements.
Yeah.
We are making observations, very precise observations of the light that was emitted shortly after the Big Bang, because that's as far back as we can see. And the hope is that by taking precise enough measurements, we'll be able to tell the difference between these two hypotheses. We'll be able to disentangle them and be able to say which one is supported by what we observe. And that's really how science happens. It's not really a popularity contest, right? It's not about like, oh, which philosophy do I like better? It's about what does the universe tell us? Like, what do we observe? And so the universe will really have the last word. The observations will.
So how do we know space is expanding?
How do we know space is expanding? That's a good question. So what we do is we observe the light emitted by the explosion of stars, for example, that are at different distances. And what we can do is we can calculate essentially the velocity of these exploding stars by using something called redshift. Have you ever heard of redshift?
Yes, I have.
Yeah.
Yes, I have.
What do you know about redshift?
Well, that's why I have you here.
Well, you've heard of the Doppler effect, I'm sure.
Okay.
And I'm sure everyone has experienced the Doppler effect, but they don't know they've experienced it. right?
But is it the Doppler effect?
It's not quite, but it's a good analogy, and we can start there. Okay.
Okay.
So you know that when there's an ambulance that's like driving by, you hear the pitch of the ambulance change.
Right.
Okay. So that stretching of the sound is produced by the fact that the thing that's making the sound, it's moving with a given velocity. Okay. Now imagine the following scenario. Imagine that the ambulance, it's somewhere away from here. Like let's say it's on campus at MSU, and we are here at the radio station, which is not on campus. So we are at a fixed distance apart. Now imagine that I start stretching the space between us somehow. Don't ask me how, but I just stretch it.
Yes.
What happens? So from my point of view here at the station, the ambulance is receding, is moving further and further away. So the sound that the ambulance is emitting would get stretched and stretched and stretched.
Right.
And so something like that happens with not with sound, but with light that's emitted in explosions of stars, explosions we call supernova. So we observe this supernova at different distances, and we compare the Doppler effect, essentially the change in frequency of the light, and from that we can infer the rate of expansion of the universe, which is controlled by something we call the Hubble constant. And then we do all sorts of other experiments and observations, of course, because if the universe is truly expanding, then all sorts of other observations should show that that's the case. So we observe the evolution of galaxies, and then we observe the light that was emitted right after the Big Bang. And all of these observations have to say that the universe is expanding at the same rate as what we observe today, right? Because otherwise observations would be inconsistent. All of the observations have to be consistent, and they are. They all suggest that the universe is expanding at an accelerated rate. It's not like we're moving away from everything else at a constant speed. The speed at which we're moving away from everything else is increasing. Okay, so the idea is that in the future, we'll be so far away from everything else that we'll lose causal contact. It'll be impossible to communicate with any other region of space because the fabric of space has expanded so much. And I know, it's hard to imagine, how can the fabric of space expand? What is this dude talking about, right?
I can't wrap my head around that.
Yeah, you can. You just have to think about a balloon, okay? Imagine a balloon. You know balloons. You love balloons. Yeah. Everyone loves balloons. Who doesn't love balloons? My daughter loves balloons. And so what we sometimes do in class, not with my daughter, is we make little drawings on the balloon. And imagine that you have 2 points that you've drawn on the balloon with permanent marker. And then you start blowing into the balloon. What happens to the points on the surface? They spread apart. They are moving away from each other.
So your frequency is going down, and you're redshifting.
Exactly.
So the theory is that as a photon travels through space is expanding. It's going to get stretched. The wavelength gets stretched.
That's right.
It's that simple.
It's that simple.
Okay, so how else do we know that space is expanding?
Well, because of this light that gets emitted right after the Big Bang. So we have the first light, we call it, right? So what happened is if you sort of play the movie backwards, play the movie of the universe backwards, then if the universe is expanding into the future, it must be contracting into the past. And as you compress the universe gets hotter, right? That's typically what happens when you compress things. So as the universe gets hotter and hotter and hotter, there's a time beyond which light can't escape because it's strongly interacting with all of the other light. It's like bouncing all over the place, and it can't really escape. So if it can't escape, we can't observe it. So there's this last scattering surface at which point light begins to move freely, and we can observe it today. And that happens, something like 10 to the minus 20-something seconds or 30-something seconds after the Big Bang, okay? Mm-hmm. And so we don't know what happened before that point in time, or earlier in time if you want, but we know what happened at that point in time. And so we can take a photo, essentially, of the universe right after it was born, and that photo is called the cosmic microwave background.
Radiation.
CMB. It's amazing, right? It's this light, it's this background of light, it's everywhere. And it shows that the universe, it shows that if you look at at space from different positions, if you want, different points in space have very similar light or background of light. The CMB is very uniform, okay? So meaning it's the same everywhere you look, and it's the same in every direction we look. So that we call that homogeneity and isotropy, because we like to give complicated names to very simple ideas, okay? So the idea that the universe looks the same no matter where we look, and it doesn't matter when we look, and it doesn't matter in what direction we look. This means that something had to connect everything in the universe when the universe was really, really tiny, so that everything could agree to be at the same temperature. Okay, it's
Right.
sort of how you should think about it. Like, if you and I are going to plan to wear blue jackets, then it better be the case that I can communicate with you and say, hey, you should wear a blue jacket to this party, and then we'll both wear blue jackets and come to the party wearing the same jacket, right? So if different points in the universe are supposed to be correlated like this, they have to have had time to talk, to arrange things such that the correlation exists. And the only way that could have happened is if the universe experienced this exponential expansion, this inflationary period, very early after it was born. And that is one of the hottest areas of research right now, trying to understand how this inflation happened, what caused it.
See, there's another thing I can't wrap my head around.
How could it have expanded exponentially? What produced this repulsion, so violent, exponential expansion in a very short period of time to produce just the perfect universe where life could arise?
So the CMB basically is ancient light.
Ancient light.
It is very, very stretched out over, 1,000 times?
Oh, more than that. It's exponentially stretched. So you're talking about seeing the universe 13 billions of years ago, right?
Okay.
So it's 13.7 or something. It's very, very old light. It's the first
But it's
light.
redshifted 1,000 times Z or K, whatever you was.
Yeah, and
1,000.
there's fluctuations in it, and there's a particular temperature to the CMB. So you can think of this light as being redshifted by a factor of 1,000 if you want, but coming from billions of years ago.
Okay.
It's pretty.
Okay, so
wacky
I got to go
stuff.
back downstairs and check on my file servers. I'll be right back.
Let's
We're
check.
gonna go.
You want some help? I
Yeah,
can
yeah.
come
Let's
help
go. You can come help me.
Okay,
All right.
sounds
So we're gonna take a quick break. We'll be right back.